Okay. Hello, everyone. My name is Diego. I'm Bauch. We're going to present this paper on the minimal degree bias in generalization on the unseen for non-Boolean functions, and also a related paper that came before. As is commonly disclosed, the title of this paper is very long, but it's actually kind of simple. It is just composed of these three elements: minimal degree bias, generalization on the unseen, and non-Boolean functions.
Non-Boolean functions, that's a funny thing. So it's a big class of functions, right? Like everything but the Booleans, like we don't like Booleans. Who likes Boolean functions?
I guess it's because they consider two specific cases of non-Boolean. Yeah.
For some non-Boolean functions.
Yeah. Then, well, what is this minimal degree bias? This is going to be unobserved behavior of some machine learning models, or rather algorithms. Okay, so people have seen some behavior, and then this generalization on the scene is an evaluation setting that we are going to define in the presentation. And then, well, non-Boolean functions is just some sort of hypothesis set. And so what this paper is doing is, it is studying some observed behavior for a specific setting when algorithms are trying to learn in some hypothesis set. Why do we care about this? Let me try to motivate this problem. So we have a hypothesis set, and there's going to be some target function that we want to learn, which means there's some domain, and our target function is going to come up from this domain, let's say, to reals, and then we have, or the algorithm has access to some training data that is going to look something like examples of pairs of input data and the evaluations of the target set. And then, well, it's going to correspond to a subset here, X-train, right? And so our algorithm is going to receive this data set, and then it's going to output some sort of approximation of our target function, right? So it's going to be something that's going to live in this space. Given that we chose, for example, a family of models, and then our algorithm is going to maybe choose one of those possible models. Now, this setting is kind of similar to the one in exact learning, as in we actually don't care about representing all possible things in this hypothesis set. We actually only care about one of them. And then I guess one approach to this could be one approach could be kind of cheating, as in, let's say this is our training data, and it seems that in these modern days companies are trying to make this as large as possible, kind of like ensure a full coverage over all possible inputs, like let's say acquire all data set in the internet and then train these large models. And then we know that we have some architectures or families of models, like transformers, for example. And we have like hardware to train these transformers, I don't know, GPUs and whatnot. And so if, in addition, we have this full coverage, whatever that means, then we kind of have some theory that says, oh, actually, this has enough representational power to represent this solution that we want, this target F star. Now, this paper, the authors kind of try to argue that this is not possible. Okay, this kind of cheating of achieving full coverage is not going to be possible, and they give two particular examples of why this is the case. This is particular in reasoning tasks, in particular for example, arithmetic. So let's say we want our algorithm to learn the addition, right? And then we could represent these inputs as sequences of bits of some length. Right? And so there are two particular problems that they point out. The first one is when we want to consider length generalization. Right? So no matter how big you make this data set, it's going to be bounded, right? So you'll have the size of this training set is bounded, which means we can essentially enumerate the possible inputs and then calculate the maximum of these sizes, right? And then we can always ask, okay, what happens when when we come with some example for which this length is bigger? What happens in this case? Will our model work or not for this? And then the second case they present is the one out, the combinatorial explosion. So even if we consider the case when this maximum length is finite and we're fine with that, if it is too large, we're going to run into problems because in reasoning tasks, we carry out, for example, in arithmetic, we carry out all these possible inputs. All of them are valid examples, and we want to get the exact answer for all of them, right? So this is going to be something very large of the order of 2 to the L, right? Where L is this maximum length, and then if this length is exponential in the number of possible training examples, this is essentially impossible to generate all possible examples. And then what they argue is we will always have like some sort of holes, in particular if the model itself is the one generating these examples, like the inputs, like we saw in the previous presentation, that the model was kind of constructing by itself the possible inputs. Then a hole is going to create maybe more other holes, and this is going to propagate. For example, we increase steadily this maximum length. So essentially what this paper says is, okay, well, these holes are unavoidable, okay, which means that generalization of some sort is required. Okay, we need this. And then the question that they make, like the whole point of this paper is trying to answer this question is the following: is given that we have these powerful models and that we can basically perfectly interpolate on this training data set, how will they behave when they are presented something that is here, that is in these holes, that hasn't ever been seen by the models? Okay, so this is the question that we're trying to answer. Now we're going to go just talk.
Yeah, I was wondering about whether a better word for channelization would be extrapolation, since you already use interpolation. Right? Like by interpolation, people usually just mean that like on the examples you have seen, you do well.
Mm-hmm.
Extrapolation is that outside of what you have seen, whether you do well,
Mm-hmm.
right? And then that would be maybe like a more, because generalization has this like lots of baggage that comes from learning theory.
Mhm.
The people hijack this concept and like, you mean like on some distribution generalization or like what do you mean by generalization? Like
Mhm.
generalization is, and especially if you already use the word interpolator, then maybe extrapolation is a better way to describe what they're interested in.
I guess, yes.
Okay.
I guess they like the word generalization, but then they try to make explicit what they mean with that.
Yeah, okay.
Which is
Let's
what
see.
we're
Let's
going
see.
to define.
Yeah, okay.
As well.
Okay, so let's formally define this. And before going to the results of that paper, like, which is for non-Boolean functions, there's a previous paper which kind of defined like these terms, and they particularly study Boolean functions. So we'll first look at the results for Boolean functions, and then we'll talk about the results of that paper which extends for non-Boolean functions. So let's define this generalization on the unseen.
Yeah, before you do that, this class is about LLMs and whatnot. So can you say just a few words of like why this paper is relevant for our class? You already said something, but like not, maybe you can say a little bit more.
I guess there are some empirical observations that when you train a transformer, it tends to present some behavior that corresponds to this bias towards minimal degree functions. It has been observed in the Boolean case, and so they argue this theory that we have developed for simpler models explain the behavior of transformers. That's what they're saying. But then that's in the previous paper, the one he mentioned. In the non-Boolean function case, they say, oh, something breaks. This explanation doesn't work as well for transformers. So it is related, but not too much.
Okay, all right.
So this was the previous paper. We
Is
will
there a
not
darker
talk about-
marker?
Sorry?
The marker is not so dark for the video.
Okay. Yeah, so this was the previous paper which defined these terms and they analyzed the Boolean functions. So we'll define what this generalization or unseen or go-to setting is. So we have a sample domain. Some x. And as Diego mentioned, we can't always scale up the training data to span the entire sample domain. So we'll always have some unseen set or unseen domain. We'll call U. And the training set is everything except in the unseen set. And in this paper, we will assume the models are over-parameterized. So we are not really interested in like learning about the inductive biases of the model, but rather of the optimization algorithm. So
I have a quick question. When you say training domain, does that mean that you're gonna have training examples that come from everything in U complement?
yeah,
Or does that mean that the distribution that's sampling is gonna be sampling from this, and you might not get some of them?
So in theory, they assume every sample is seen, but
Okay.
in the experiments, in some of the experiments, they sample from
Yeah.
this. Yeah, so we assume the training error is 0 for all the models. And this go-to is defined as follows. Yeah, so for some target function and the function outputted by the optimizer and the unseen set. So this generalization or the go-to is this expectation. this represents uniform sampling from the unseen set. So we take elements from this unseen set and evaluate like the loss function for that element, and the loss is computed over the target function and the function trained on the training set.
Why do we care about the uniform distribution here? What justifies that?
I think we want to, I'm not entirely sure, but we want to cover every point in the training set, so we uniformly sample from it.
Isn't that the test set?
Sorry, oh yes, sorry, test set.
Yeah, my guess is that is irrelevant. Like maybe that makes you have to choose some, and that's one that ensures that you hit everything. But probably the proofs follow through with a different that it has the same property.
Yeah, maybe it's the weakest. Like, it might be the easiest to achieve this. Like, this is the weakest requirement, because I mean, if I can choose this distribution, maybe I will choose it adversarially, and I will focus on one example where everything is wrong. So that would be kind of exact learning, right? Like on one example you're wrong, then like you're dead. So these guys are like, oh, I'm going to be nicer to the learner. Nice and not nice, because it's not nice that you're not showing some examples. It's like some part of the input space is definitely not going to be covered. And then you're going to be tested on those, but at least you choose a uniform distribution there, which is maybe less harsh than if you would say that like the largest error that the model makes on unseen examples is what I care about. But it's sort of like this uniform distribution is maybe not so innocent. Like people, I think a lot of times are very quick to jump to the conclusion that, oh, uniform distribution is good. It's like, it's benign, it's somehow, it doesn't have any bias or whatnot, but like, it's kind of weird, because if I copy an input from the unknown domain, like little u, and I make a zillion copies of it, then the uniform distribution on this new domain is going to put a lot of weight on that single u. So it's like the structure of the domain is going to play a big role in this. Like uniform distribution has no special, meaning on any of these domains. So you got the illusion that you are not, like you're choosing something that's not specific to your thing, but like actually who knows? It could be anything. It's like.
But didn't your example just counter the point of why it's actually not that bad of a choice? Because if you want it to be adversarial, then you could be adversarial through the unseen domain by making it like heavily focused on certain things.
But I'm saying that the uniform distribution doesn't save you from this, I guess. Like a
Yeah, it
follow-up
doesn't.
to that is
Yeah.
that because if I can choose the domain U adversarially,
Yeah,
then I will do this copying of a
Yeah,
single element
exactly.
a billion times, and then
yeah.
it's dead anyways.
But then that means that if you do well on this, on the uniform distribution, then that means you can basically do well on any
Right.
distribution.
Yeah.
As long as
this copying was not really changing what the algorithm is doing, but it should not, right? Because the algorithm has no idea
Yeah.
about this unseen domain,
yeah.
supposedly.
Yes, so I guess that they don't really do any claims about the generalization being good or bad for any model. They actually never use this distribution, because what they want is to understand what are the solutions you find before I even evaluate you. You're going to be biased to find some solutions,
Yeah.
and in some cases they will correspond to the actual F star, in some cases it won't. And then because of this bias is that you're not converging you're not behaving correctly in these holes that you have not seen.
Sure.
I guess another thing is this is like basically just saying like if you were evaluated on a distribution that has a totally different support than your training distribution, then how would you do? But also I'll give you all of the data points in the training set and it's realizable.
It's kind of.
I guess that this is something.
There was no hypothesis set yet. So it's more like we're gonna study the bias of some specific algorithms.
Yes, like I guess
It's
this
more like an inverse, like, okay, like gradient descent does this and that
Mhm.
on specific settings.
Mhm.
Yeah.
Yeah, I guess this gives you like a hardness metric for some use,
Right.
Mm-hmm.
but actually they never really go into which use we care about.
Oh, okay. Yeah. Let's see the results. Like, yeah, I guess maybe I'm just like jumping too much and like why this is defined this way before seeing anything.
Yeah, so since we can't scale up the training set to the entire sample domain, so the training set that we have considered could have some special, like say unwanted structures. Say for example, so our training set would be all, but every first bit is like 1 in every example that we see in the training set. So in this case, like, so all functions of this form, this is the true target function plus x1 minus 1 times any arbitrary function of x. This is also valid, this also achieves 0 training error on the training set. So we have a set of interpolators in the training set, and what this paper tries to understand is like, does the optimization algorithm has any bias, like which interpolator it will converge to, and we want to understand that bias. So for that we'll define some terms. To analyze these functions, we write it in some basis expansion, and this particular this paper chooses this particular Fourier Walsh transform as the basis functions. So which
we have
is
already seen. Which we have already seen. Parity,
Yeah.
blah blah blah.
Yeah.
It's like everyone chooses this. I mean, like it makes sense. Like this is the sensible way to write Boolean functions. It looks really fancy, but like it's really elementary. And then you say Fourier, Walsh, and like, wow, okay, like those people, wow, oh my god, this
That's-
must be higher math.
Is there a reason why people don't just talk about eigenvectors? Or
What?
is there a reason why people don't just talk about bases instead of transforms?
I mean, like, of course, like in, yeah, like if you're not in a Boolean domain, then maybe things are a little bit fancier there, and then this Fourier Wash does mean something here. It's like, I don't know, something ultra simple, but fine.
Yeah, so
Anyways.
this is the coefficient and this is the basis function, and like, let's look at an example, which is the majority function over 3 bits.
Yeah, if you have never seen this, like this is like magic, but yeah.
It's magic to me right now.
Oh, but you have seen it, no?
Probably, I don't remember it though.
Okay, that makes sense.
So this just outputs the majority bit. So if you have all ones, it will output 1, and 1 minus 1 minus 1, because majority is 1 and 1 minus 1.
Oh, I remember now.
Minus 1 and so on. Because permutation invariants are not right other terms. And it turns out that the Fourier Walsh transform of majority function is this. Probably verify. If everything is 1, this is 3 minus 1, 2, and half, which is 1. 1, 1 minus 1 is like 2 minus 1, and plus 1, again half, which is 1. And 1 minus 1 minus 1 is this is minus 1, and that's also minus 1, and again half, so it's minus 1, and so on. So once we write it in this expansion, we can define degree of some functions. And the degree is just the maximum degree of the monomials present in the expansion. So degree of majority function is 3, and it comes from this term. And now is the important definition. We define something called as degree profile. So degree profile for a function is a d plus 1 dimension vector, and it's nothing but the like vector of densities of these coefficients. So I'll write it formally and then I'll give example.
Is there some intuition of how this basis, whatever expansion thing was chosen? And what is f hat?
So f hat is the coefficient, so it'll be just
How do
half.
you define the coefficient in general? Maybe you
Oh,
can just
right.
write it down because you haven't.
Yeah, it is just the expectation of the dot product.
It's just the projection or the vector. So you can understand as vectors, and you're projecting, you're taking the
Yeah.
component or that direction. Which in this
Every
case-
function is just a vector in a high dimensional space.
I
All
know,
domain
but-
is 2 to
Yeah.
the d-dimensional.
Yes.
You take all the you take whatever basis functions for 2 to d-dimensional
Yeah.
space,
Yeah.
and then you just like expand everything in terms of that.
Uh-huh.
And the basis functions, because you're on the Boolean hypercube, you
Mhm.
can choose them to be such, and those are orthogonal with respect to the uniform distribution. So it's like just the natural add to structure and the uniform distribution.
I will make a picture later.
Okay.
Yeah, so this is how we compute the coefficient. And coming back to degree profile. So this is just the summation of densities for a particular degree. So you can formally write that. And like we can compute for the majority function, I think that's the picture here. So the degree profile for this majority function is like, first we look at the highest degree term, which is minus half. So it will be 1/4. There is no degree 2 terms, so it's 0. And degree 1 is these 3 terms, each with coefficient of half. The square of that and like add it 3 times, so it's 3/4. And there is no constant term, so it's 0. So once we have a degree profile, we can define this comparator for functions. So which is like degree profile of f is less than degree profile of g. If it's basically the lexicographic ordering, so there exists some index I for which this is less. Degree profile of anything index for f is like less than that of g. And for all j less than I, this is equal. And once we have an ordering, so we can finally define this minimum degree interpolator or extrapolators.
So you said a few things, like you said that this is a density or something.
Yeah.
When is this at the, like, okay, so by density, you mean these numbers sum to 1, so it's a probability vector, right? You mean that? I'm just asking what you mean by density.
Okay.
I'm pretty
I'm
sure
not
you
sure.
just mean that they sum to 1.
Yeah, I'm not
Right.
sure if it is some to one.
They will sum to 1
Okay.
under one condition. What is the condition? The condition is that if you square the value and you take its expected value, it's 1. You're normalizing the function such that its expected energy is 1. The expected energy is 1, and this is going to be a probability vector. Why? That's called Parseval's theorem. Right.
So that
This
holds
is
in,
where Fourier and whatnot comes in.
that holds in general.
Yeah, that will, like, more generally for these Fourier kind of transforms, which are very similar to this. Like, you just take some autonomous basis in an add to space, and then you correlate the basis with the function. Those are coefficients. So you're expanding the function in terms of those coefficients. Then Parseval's theorem says that the sum of the squares of these coefficients is equal to the energy of the function, the sum of the squares of the values of the function over the domain. So that's a general theorem. This is a special case. And proving that is not that hard if you set up everything, then like it's just algebra. After all, everything is equal to everything, so how hard such a proof can be,
Mm-hmm.
right?
Yes, so essentially these bases that you're choosing is orthonormal.
That's
so its
right.
norms are one. And when you do this transform, which is just applying the matrix, what you get is still the same magnitude. So if your input f has norm one, the norm of the transform is also going to be one.
That's right. Just the only thing that's weird about it is that the vectors we're talking about it are not from dimension d, not dimension d, but 2 to the d, right? Because that's the size of the domain. And because of that, it's a little bit unusual to think about the bases of this 2 to the dimensional space. And you could choose many different bases. This is one of the bases that I choose. Like these BTX functions, they're just big vectors.
Mm-hmm. Can't you always choose the basis that's only equal to one when
You
a
could
particular
choose,
set of
yeah, like the Euclidean
settings
basis would be
are one?
another choice, right? Like 1 and all
Yeah.
zeros everywhere else. You can write everything for that, like this coefficient, blah blah blah. Then what you would say is that you're just
Yeah.
tabulating the values. You enumerated
yeah.
the domain in some way, and you are not kind of, yeah, I guess it just ended the way. Like, it's a 2 to the d-dimensional vector space. You have many bases for it. This is one specific basis. Why do we love this basis?
That's a good question.
Yeah. Why do we love this basis?
I guess one intuition is that they have their frequency corresponds to the size of the set they are capturing. So precisely you're kind of ordering them as with respect to how much they change.
Right. So somehow the bases that
Somehow, yes, choosing
we
that
have-
basis is what results in the bias. It's a similar intuition as how when we have the continuous setting and we consider the Fourier transform. Like the initial one that you choose is like a constant function, and then the next one is just like one single oscillation, and then you get faster. That frequency is like here the size of the set t, and then that makes like it would explain why we choose these particular bases, or for example, or the one Vlad is proposing.
Right, right. I think that the connection to actual Fourier and frequencies is really interesting, and that somehow is at the heart of this. But it might not be apparent for everyone why these particular bases really correspond to kind of waves. Like, where is the wave structure encoded in this? I guess for that you have to think about like, what are waves? Waves are like, you have constant portions and then changing portions, and like these functions, these sparse parity functions, kind of have that structure. You change certain component of the input, the function doesn't change. If it was not in T, it doesn't change. If you change the component that's in T, then it flips a sign. That's like, you know, like, it's like if you're thinking about like, oh, like a sine wave, it's like high, low, high, low, high, low. So that's like the discrete counterpart of like changing. And then how many changes you have, like if you consider the parity function with the sparse parity on T, then however is the coordinate of the T, that many changes you will have. If T is the whole thing, then it has changes everywhere. If T is just like one element, then it's kind of lazy. It only has changes if that particle will be changes. So that's like low frequency, like not many changes. High frequency, many changes, like changes everywhere. That's sort of the intuition, I think. If there is any intuition underlying any math. Okay.
Yeah, so we can define what min degree interpolators are.
Cool. So, I don't know how many people understand this Fourier business with the waves. Of like, why do we care about that?
I don't know.
Because like we reduce this intuition to the real Fourier stuff with the waves, but no one explained what that means and what's the intuition behind that. What happens is that if you have functions that are kind of smooth, then if you write their Fourier coefficients, they decay faster. So it's like a characterization of smoothness is how fast the Fourier coefficients decay. So in a way, like it captures our notion of like how smoothly the function changes. Same here, the coefficients decaying fast. Like for high frequencies, you got a lot of zeros. This is a lazy function. It's not really changing. So it's all about this smoothness. And in a way, like as we're gonna hear, like it's somehow easier to learn functions which are smoother, which is not surprising. If you think about the real valued case, like, oh, the function is not changing that much. It's like constant approximation kind of going to get it. It's like, it's easier to learn. So this is sort of the intuition behind this whole thing.
Isn't it the same with polynomials that the coefficients
Yes.
are also decreasing
It's not quite.
for Taylor's, whatever?
No, not at all. It's like
it's smooth.
if you just take the polynomials like that, the coefficients are going to be wide. Like you can have a very smooth function that you try to approximate, and like if you take the interpolator, Lagrange interpolator, for example, the coefficients can be really large for a very high degree, and they all add up everything, and it's
Really?
it's not very necessarily very good. And then there is Chebyshev operator, like, okay, let's not get into polynomials, but you can tame polynomials, but it's a lot of work
Mm-hmm.
to make them behave better. But like the standard Lagrange interpolators, it's just like not a good idea.
But still, the degree corresponds to the smoothness. No?
No, not really, not really, because they can cancel somehow and like, no, it's somehow okay. So you can say that higher. Okay, so you take the function space spanned by polynomials of degree d, then if d is larger, you can approximate more functions better. And the rate at which you can approximate, let's say, smooth functions with d degree polynomials, it actually corresponds to the same as with d Fourier coefficients, like no real difference between these spaces in that sense. But if you're too naive about how you're choosing, how you're approximating with the polynomials, then you run into trouble. Whereas with the naive thing, which is like this correlation of the waves with the function, like that's the R2 thing, that works pretty well. It doesn't work that well. You can even improve on that. And like this is what approximation theory people do. Okay. And then we go back to machine learning, right? Mean degree interpolators.
Okay, so we can define the set of interpolators for a given target function and the given unsigned domain as follows. So it's set of all functions that agrees with the target function on the training set. The min degree interpolator is the function with the minimum degree in the set, and minimum degree is defined using that. So to give an example, let's consider this target function over some d variables, but it's just equal to the product of x1 and x2. And suppose our training set is such that either x1 equal to 1 or x2 equal to 1 always in every example. So this essentially means like x1 minus 1, x2 minus 1 is 0, or x1, x2 is equal to x1 plus x2 minus 1. So this function agrees with the target function on every training sample, and this one is a lower degree than this. And the result is that the SGD or gradient descent prefer like lower degree like interpolators, and we'll see why it is.
Is this the same thing about how double descent works? Where the whole, because like here we have that the function, like sorry, that the architecture or function we're using is like really high dimension that we can interpolate perfectly, and there's a lot to choose from.
Mm-hmm.
And then the question is like, which one do you pick?
Mm-hmm.
And it seems to pick the one that's like low whatever degree bias, which is what I remember that happens in this whole double descent stuff, right? Where like the choice of interpolators is the one that has, but there was like the lowest normed weights or something like this. How is that different from this, is what I mean?
I think it is related. Like people have tried to analyze the case with deep neural networks in, like not the Boolean case, but like general cases, and then they use the actual Fourier, they get similar results. But I'm not sure if that's what happens in that double descent or this grokking, that you just keep training for very long, and then eventually it seems to converge to those solutions as well. But I don't know if it's because of the same reason that happens in this case.
Sorry, I missed that, but why we assume x1 equals to y or x2 equals to 1?
Just an example.
Oh, okay.
Why is the parameter the unseen data?
Sorry?
The main degree interpolator, it's f star and u, should that be?
Star, right?
Yeah, that.
I guess it's just notation you could write you
Oh, okay.
complement.
Yeah, I mean, U is the unseen and U complement is the training set.
Okay.
You can write it that way.
By the way, you didn't define the mean degree interpolator yet. You defined it set
Oh,
I f star u.
Okay, I can write it down.
Maybe you want to define it.
Yeah.
Is that just like,
It's gonna be one of those functions that gives you the mean degree, something. In the degree profile, I think it's like the lexicographically smallest.
Yeah. Yeah, it's just that. So MDI is function belonging to this set, right? Such that
It's kind of clever.
for all other G belonging to it.
oh,
So we just pick the one with the lowest.
and why do we care about that, or is that going to be explained?
We'll see why it matters.
So that's like if the learner picks the smallest one.
Yeah, that will be the result. I hope, we hope that like some learning algorithms do have this bias that they pick the mean degree interpolator.
Okay.
Right? We are working towards that.
Yeah.
And it's really meant for the whole degree profile, not just.
It's like a very interesting thing to study though, because when you have these very over parameterized models, it is interesting what interpolator they do pick, right?
Yeah.
Like in some way, isn't this kind of like studying this whole of like thing of like what happens when you have over parameterized models? You know, like in classical statistics, people are like, oh, you don't have enough data, whatever.
Right.
And here
Yeah,
it's like,
same
oh,
thing.
if you're if it's really over parameterized relative to data, there's like so many possible choices that fit the training set perfectly. Like, how are we going to pick between them?
Yeah.
Right.
And this is going to say that this is maybe a good idea or something.
I don't think
No,
it says it's a good idea.
Yeah, no, it's
Oh,
just,
just saying this is what happens.
It's going,
Oh.
it's going to pick them.
Oh, okay.
It's a descriptive thing.
I
Yeah,
see.
yeah.
Like the
But-
algorithms that we love
Are doing this.
are
Yes.
doing this.
Yes, exactly.
Whether you love this or not,
Oh, okay.
they're doing it anyways.
Oh.
Okay, so I'm going to mention these theoretical results. We're going to use some elements to consider, which are specific domain, hypothesis set, the model class, and we're going to choose. Oh, actually, I think, yeah, we have to define the models that we're going to consider.
So the models that are considered in this paper, first is random features model, which is
Oh, there we connect to double descent. Because like really easy to argue for double descent with random features, which is a little bit smoke in the eyes. But
Hmm.
so AI is the only learnable parameter, and this feature is like for some activation function. So yeah, and this weights and biases are randomly sampled. So, like one reason they give in the paper why they chose this is because it kind of approximates neural network in the NTK region, and the other model that they study is linear neural network. So this is just a typical neural network, but with identity as the activation function and transformers, but only empirical results. And this is only like encoded only transformers with blurred positional embeddings. So these are the three models.
What's the difference of a model or a hypothesis set, or a model class and a hypothesis class?
This is where the possible target functions live. This is what can be represented with the models that we choose, which is not necessarily simple.
Okay.
Particular this.
So it's what your learner is going to be searching over, and then the hypothesis class is what functions are labeling stuff.
Yeah. Yeah. And we also have an algorithm that is going to pick among these models. Okay. Yeah, so I'll just specify them. So the domain that we have is again sequences of bits of length A. The hypothesis set is going to be our Boolean functions, but such that f is going to be a p sparse function, and this is essentially from the original input, the strain of the bits. Only p of those actually are relevant to determine the value of the function.
So is that the same as saying that the number of bases you need is going to be 2 to the p?
Is sorry, what number?
2 to the p? Like if it was d sparse, then you'd need 2 to the d bases, but then if it was smaller, then you only, I don't know. How do you actually say this? Like, what does it mean that only this many matter? These many indices?
yeah, what is the meaning of p sparse?
You can define it.
The Fourier coefficients are always non-zero except for p, or
So it's p sparse if there exists three elements. One is p, which is going to be less or equal than d. Second, there exists a subset of a subset of the
Dom,
the
dimension.
Just the all
Right.
possible
Components.
indices.
Yeah.
So it is going to look something like this: I1, I2, and so on to some IP. It has size
Yeah.
p,
Yeah.
and then there exists some Boolean function. But this Boolean function,
Okay.
this Boolean function is only taking into input p bits, such that the value at some x is going to be the same as the value of this
Uh-huh.
other function h in those bits inside this index. So
Mm-hmm.
one is two and so on. Let's say and this is for all x in the. Okay, that's p sparse.
So that also means that if I do the Fourier expansion and t is not overlapping with this set I, then the coefficient is 0.
Yes.
Yeah.
Mm-hmm. So you need 2 to the p max bases.
Yeah.
Well, only those bases are excluded which are in the complement of I.
Yeah.
Those are, yeah, I see. It's like d minus p.
Yeah, or
2 to the
excluded.
d minus p basis functions are excluded.
Oh.
Yeah, I think it's bigger. Cause they're all zero. Yeah.
Yeah, those are all 0.
Uh-huh.
All the others could be 0 or not
Right.
0. Like a little overlap
Yeah, yeah.
can make the coefficient
right.
not 0.
Maybe it's the other way.
Okay, so the models that we're going to consider are the union or weights and biases of these random feature models. So this is just all this possible F.
Nice.
There are parameters by weights, biases, the trainable parameters, and an activation function, such that this activation function is strongly expressive up to p. This term I will maybe define later. I don't think it's that relevant, but what is important is that we are considering a specific sort of activation function. And then our algorithm is going to be defined by 2 steps. The first one is we're going to sample weights and biases. In particular, in this case, it's just how bias is specified here. So just uniform normal distribution. And then the second one is the algorithm given the training set is going to output the among all those possible interpolators captured by these models and parameterized by weights and biases sampled here. Those that correspond to the ones that minimize the norm of trainable parameters.
The
So-
norm of what? What's that in there?
Trainable parameters.
So
Oh.
our random feature models have these parameters
Oh,
used to
A's.
combine the features, right?
Yeah, yeah.
And so,
So now this looks really close to this whole minimum, like sum
Yeah.
of 2 norm
Like the
solution is
double
chosen.
descent
Yeah.
stuff.
Basically, like the choice of weights is the one that has the minimal 2 norm.
yes.
Where is
then-
this related to the degree bias?
Oh, that's the theorem.
It's
Oh.
coming.
Yeah.
And wait, and I guess the strongly expressive thing is something like M is kind of a superset of H. Like it can
Uh,
represent everything in H.
No, it's essentially that you are not going to lose the information of the elements in the basis that have at least size p.
Uh-huh.
So we have like this basis
Yeah.
of Fourier Walsh
Yeah, I see.
transfer elements,
Yeah, yeah.
Mm-hmm.
and then if we choose like wrongly these features, they might cancel all of those. They might don't get any projection over those elements.
Mm-hmm.
So we couldn't represent. I guess we will be losing these components
Yeah.
of size p, and this is telling us, at least for all the subsets of indices, all the t's with size less or equal than p, we can capture them.
Yeah. But isn't that basically saying that for any, but then that means every function in H is also representable by like these the Fourier things up to whatever degree
Yes,
p
like
or something?
it doesn't specify what happens with numbers larger.
Yeah.
It just specifies that at least you can guarantee p.
Yeah, but that's because things in H are of this form, right? The hypothesis set. Aren't they? Isn't that the whole point of it?
Yes. Okay.
And so basically you can represent any function labeling your data from H.
Yes.
Which would mean that that set is non-empty, kind of.
Yes, and that's a result of the theorem. Yeah.
I'm really confused.
Mhm.
That said random feature, is there a randomness here or not?
Yes.
We are enumerating all W and.
I'm
okay.
specifying
But
that
like
in the
whenever
algorithm.
M is defined, the W and the B, there's just like you take union over those.
This is just my way to say that we're considering all the possible feature models, all the random feature models,
Okay.
but then the algorithm is going to pick one sort of weights and biases.
Right. And you only require, you require that if you consider all possible W and B, then somehow this is a sufficiently expressive class.
Mhm.
Like there is no randomness in that requirement, in that definition. I couldn't read this WB and then there is an A and a gamma, or A gamma, or. What's that?
This is just my way to say it's going to choose among those interpolators
Okay,
that the random feature models can represent,
right.
given this unseen set, and that we sample these specific weights and biases.
I see. Earlier, when you were writing this strongly expressive, in that line, there is some A, like F, R, F, blah, blah, blah. Yeah, I couldn't read that. What's that? Oh, that is a sigma.
Yes, you see. So it's the activation function.
We are also, sigma itself is strongly expressive. The activation function.
The activation function, yes.
That's a real-to-real function.
Yes, it's a real function.
When do we say that sigma is strongly expressive up to p? I know you already said it, but no, I'm confused.
About the
What's the definition?
definition, I haven't defined it explicitly.
Yeah, but like you can say it with words.
Essentially, you can think of
That if you're setting the W and an X and a B in the right way, W and a B in the right way, goes into the sigma, then you consider all possible such things, then I don't know, all these p sparse functions can be represented with linear combinations or something. So we take the Fourier
Essentially, we want
of the
this
phi, okay?
to be non-zero for this such that
Every W and B or
sizes.
just some W and B?
in
Or some.
expectation.
On expectation over the distribution of W and B,
Yes.
the Fourier coefficient should be non-zero.
Yes. Actually, they define it with some bound. This lower bound. We want this term.
Bounded away from,
We want this term. So this is the lower bound that they choose to
D
define
to
this
the,
strong expression.
D to the,
Size of t minus.
what's in the
Minus
exponent?
size of t.
Minus size of,
T is the subset of indices that is defining the basis that you're considering. This T,
uh-huh. So we are considering, like there is a sum over all possible T there,
all the T's that have some specific
size.
size. Yes.
Okay, let's call it, I don't know, S, like size.
Mhm.
I see, and then D to the minus size is what you would have there, but it's only when the size is less than or equal to P.
Yes, exactly, and that's why
Okay.
it's up to P. Because these features are function of our activation function, right? So essentially we want to guarantee that we pick correctly the basis, and this picking correctly is like taking the average over
Uh-huh.
then we are sending some energy to those bases of the
Uh-huh.
corresponding to sets of that size.
Yeah, I see.
What do we mean by energy? Because I know.
Like it's a square, expectation of the square value.
It's basically just
some
this term.
function.
Okay.
That's energy, it's like.
Because
It has
energy
axis.
comes from the physics perspective of signals, when actually it's like energy.
It is, somehow.
Oh, okay.
And people started talk on this crazy language, even math.
Well, what else are you gonna call it?
Yes, you have to call it some. Yeah, some.
Okay, so good.
No, I understand.
Now
It's like we
trace
call
the theorem.
So C is strongly expressive up to.
them mass functions and density things. Like, isn't it the same story?
Okay, so this is somehow a picture. We have some set of possible functions. This is, let's say, our hypothesis set. F star is somewhere here. Okay, and then we are putting some model class that is able to represent, let's say, these possible functions. And then, given some, let's say this is the domain, given some unseen set U, this is going to specify some possible interpolators. Right, so this is-
Mm-hmm.
And then that means that this set here is the possible interpolators that we could represent with our
Uh-huh.
model choice. And then
Which is apparently not empty.
Yeah.
and then we have some algorithm. That algorithm is going to give some preference to the subset. Okay. And then question is, what is this? What are these interpolators? And so the theorem is as follows. When the number of features that we're considering goes to infinity, we have two things. The set of interpolators that our random feature models can represent is not empty. Okay, so
There you go.
there exists something.
Uh-huh.
This purple section has something inside. And then the second one is that the distance between the set of interpolators that our algorithm picks and the mean degree interpolators is equals to an epsilon term that depends on the size of the sequences that we are considering, such that we take the limit of this error term, let's say this vanishes, it goes to zero.
What is the sequences we're considering?
Those are the sequences that live in the input domain. So when you consider something
Oh,
that has
sorry, I forgot what D was
infinitely
completely.
long inputs,
Yeah.
then the distance between this blue region, the selections that our algorithm does, and the mean degree interpolators that we defined before,
Mm-hmm.
is going to tend to zero.
I'm very confused now. The reason is because U is a subset of the d-dimensional hypercube.
Yes.
So it could be a different subset as you increase the hypercube, like add more dimensions. Is there some regularity assumed about like how this U changes as you're adding more and more dimension, or the target function also changes and like?
Yes, so they assume that some of the key information corresponds to the p bits that are necessary to specify target function. And this p is going to be actually constant with respect to the length. So what they're saying is the number of bits that you
Oh,
need.
it scales linearly with D.
Sorry.
P is scale. P is alpha times D. It's like a fixed proportion of
Oh,
D.
sorry.
Is the sparsity or is it O1?
Yes, O1.
O1.
Yeah.
It's extremely sparse.
Yes.
It's like
So
vanishingly sparse.
Yes. So that's
Okay.
fixed. The number of bits you depend on is fixed, but then the length of the sequence can be infinite. And in that limit is when this happens.
Okay. So basically, if you you have the P relevant bits of a single target function somehow, and then you're adding irrelevant bits more and more and more, and then that's the limit that is being considered there.
Yes.
And how is the training set relates to this? The training set is fixed. What is it? Does it grow? Like, does it include all the relevant bits? Like, what do we learn about
I
this?
guess U is specified.
Yeah.
I guess you have to specify U
Yeah.
for each D.
Yeah.
Yes.
That's what I mean. Like, how do we do that? There must be some structure there. They must be doing something with that, because otherwise I could be very mean.
I don't remember any specification in the paper of how do you construct those U's.
Okay. So then this is a question for follow-up for next class. You answer it next class.
Or reading carefully.
What?
Yeah, or reading it carefully.
Well, not me. He.
No, yeah.
Or you. It's alright, but I'm really curious, like,
Yeah.
some things must be going on with this U.
Mhm.
Yeah.
Like basically you're saying that the test set U cannot be chosen in any arbitrary way, or in other ways, like your
Right.
training set can't be giving you no
Some-
information
some
about you.
consistency over D, like increasing D, should be happening, because otherwise, what are we talking about? Like, you can lose all the information about your F star. Like, I add a lot of irrelevant coordinates, and like, all my examples are gonna show no relevant bits of the target function, and then like,
Mhm.
okay, that shouldn't work.
Yeah.
So there must be some assumption. I assume that we just assume that the relevant bits of F star are shown, like that part of the domain
Mm-hmm.
is shown, and then some irrelevant bits here and there, and it doesn't really matter what you do with the irrelevant bits.
Mm-hmm.
As long as you show the relevant bits, you can blow up things like that, and then those things are happening. This is my guess, but
No, some
No.
of the relevant bits are also hidden.
huh?
Some of the bits that are necessary to calculate it
Are also
they
hidden.
are also hidden, yes.
Okay, but like the hidden
But the numbers also
consistently or
constant.
something, or yeah, like if I start to hide even more, then like I don't know, like maybe it doesn't matter. Maybe it actually it just talks about that as UD is getting large, but I can keep it small. Like, why is this going to 0?
The sequence.
No, yeah, like this epsilon d, like this is the distance.
Well, we're
of
also
what we
talking-
choose, and the minimum distance interpolator, whatever the distance is. How is the distance defined, by the way? We're measuring distances between,
Actually, they don't define it, and in the proof, they have some error term, and then they say it's not even this term, but that term
is something
you
like
could massage that term, and you could express that in this. If maybe you choose the L2 norm in parameter space.
Okay.
It's just like
I wish machine learning people would write papers where in the theorem statement every term is defined. It's a
We've seen one
bit
like
of a
that earlier.
wish. Yeah, but it's
And one particularity of the Boolean case that I think Babish mentioned is that the MDI, the minimum degree interpolators, actually correspond just to a single point. And so in general, this point is not going to correspond to your target function, which means most likely you will fail to learn the thing you want to learn.
Mm-hmm.
Okay.
sure, you were not given information about it, you don't learn it.
Yeah.
But it's like a best effort kind of thing.
Okay,
But here, the
you-
distance thing is just asking how close do we get to that, even though that minimum degree interpolator might not even be a good choice relative to F star.
Yeah, who knows what it is.
That depends on the U that you choose.
Yeah.
Okay.
But it just says that like this L2 regularized interpolator with this random free
Yeah.
thing automatically is doing the same thing as if you computed the
Yeah.
minimum degree stuff.
Yeah.
The algorithm has this bias.
Yeah.
And the reason you talk about this is because kernel interpolation people do this or whatever.
I was going to give you a picture, but maybe it's too late for that. So maybe it's better. So, as you point out, there are some issues with this regime. They call that a regime, which we are like considering this limit when we make this arbitrarily long. And then in this paper, they consider a secondary setting, a secondary regime, when this is not necessary. Okay? So.
I see. When we don't have to blow up the
Yes,
size of the
yes.
domain.
Because
Somehow the magic happens because somehow the domain becomes really large. And that's sort of weird, like why do we need the domain to be really large to say something about what this algorithm does. Yeah, I guess.
I'm not sure if it's related with the size of the domain, but we will see.
Dimensionality of the domain. D.
Okay, yeah.
Yeah.
Yes, and I guess the reason is that empirically you can observe that for small d's, the same behavior happens.
Right.
So that's
Yeah, so in Boolean case, we saw that STD chooses the MDI interpolator, but what happens if the functions are non-Boolean? So that is the result, I mean, what this paper studies.
Mhm.
So let's look an example first. So let's consider the target function, which is constant, and our training set is such that so this is the training set, and they choose the activation function as this particular thing, and they have also tried for a couple of more such polynomial things, but it turns out that the random features model converges to this function as n tends to infinity and d tends to infinity. So for this example, the MDI was the target function itself, but it turned out that it converged to something else. Like it's not even the target function and not even the MDI. And to analyze like what is happening,
What is the MDI?
MDI is just the target function, like that's the minimum
Oh.
degree. Like, one.
This is the case when this is actually the same point.
Yeah. So in the earlier case, we considered this sparse regime, which is nothing but.
Okay, just a little question. So we are in over RD now?
Yeah, so we are considering like non-Boolean functions.
Okay.
So
Every function over the Boolean hypercube is considered a Boolean function, real valued or not. Because the previous result, this one, for hypothesis set, the outcome was also plus minus one. Those are classically what's called Boolean functions, but you could also have real valued functions. For the coefficients, everything is defined for those as well. You can do everything. But here you're also changing the domain, right? Then I'm really wondering, okay, so if you change the domain to RD, did you change the Fourier basis?
Oh yeah, so here they use Hermite, some other basis expansion, like Hermite basis or something like that.
Right, like
Hermite
That one,
polynomials.
yeah.
why would that be like there are like a zillion orthogonal basis over RD?
yes.
Yeah.
Yeah, like why would why would that work? Yeah, I don't know. Okay, I see. Okay.
It is, they just start motivating why we want to consider other settings as in.
I know, but like
Let's
this
see.
is a little bit like you're motivated as a motivator if the basis is not the natural basis. If I choose the wrong basis, it can be a minimum degree interpolant in that basis, but not a minimum degree interpolant in the right basis. And then like, okay, like this is not a counterexample to that. This doesn't even converge to a minimum degree interpolant because, well, it could be a different minimum degree interpolant depending on what basis we chose.
Yeah.
Anyways, moving on.
Yeah, so the earlier setting that we considered, like in the Boolean case, where the weight side bias is where sampled from this. And F star was assumed to be OD1 sparse, and D tended to infinity. So in this paper, they introduce a different setting called small features regime. Which is defined as follows. So here the D is fixed, so we don't blow up the input dimension. And we only make the features small. epsilon tends to 0 and the input dimension is fixed. And it turns out that in this setting, even non-Boolean functions converge to MDI. And in the paper, they show the equivalence between these two settings. How this, like doing STD on this setting is equivalent to doing STD on this setting plus the regularization term, and that regularization term is the one that is making it deviate from the MDI setting. And we'll see the proofs. Why is that so?
Okay. I see. What's sigma here?
Which one?
There must be a sigma somewhere. It's not written, but the W and the B were used
Oh, yeah,
inside
I think
this
it's
transfer
we are,
function
yes,
sigma.
we are showing the same models. It's random feature models.
Yeah, it's still the random features.
Sure, but like what is the sigma?
I think it's the same assumption still.
No, it's going to be even more strong. It's going to be polynomials. We're going to assume sigma is a polynomial.
Sigma is a polynomial?
It's a polynomial.
Some polynomial?
Yeah.
Okay, so a polynomial transfer function. I see. Because I was wondering like what's the meaning of small? You know, like if sigma can do an arbitrary thing, then like, I don't know what this small means.
Yeah, it's polynomial.
But it sort of does mean that like the W and the B are close to 0. You're taking inner product with X, it's a vanishing vector. Then it's like everything, like you only care about how sigma behaves at 0 effectively, because both W and B are becoming really small. So I see kind of funny games that these guys are playing. Right.
Cause like they're basically just choosing it to be close to 0.
Yeah. I mean like when you do these things, like you scale this way, you scale like n, and like then yeah, funny things are happening. What looks nonlinear becomes linear, stuff like that.
What do you mean with what is nonlinear comes linear?
Because I mean, like you take an arbitrary sigma, you take its linear approximation at 0. That's the behavior that you're gonna see from here. And so if you had a linear sigma, and you have this random feature model, then you can calculate exactly what things are going to be in the limit of large N.
Yeah.
Because then you have central limit theorem and like all of those fancy stuff. I guess this is what they're gonna do for the proofs.
They don't really
Expand them.
do much with the sigma. They do use the strong
Law of large numbers.
strong law of large numbers, so they
Okay.
get log some kernel,
Yeah.
and then they analyze the
Right,
kernel.
right. I see.
But they don't really use linearity of sigma in that limit.
Okay. 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 Let's see what's happening.
Okay, so in this case,
We don't have much time. But we started late.
so these two regimes they are going to consider now in the real valued polynomial case. So in this case, our domain is just some Euclidean space, R2A, and then the hypothesis set. So like we'll have two of them. There will be one for the small features regime, which is just the polynomials up to degree p.
Mm-hmm.
Then there's going to be one for sparse target, which is just a function here, so a polynomial aptly repeat. But again, with this constraint that such that f is sparse. And our model class is going to be the same, except that now sigma is a polynomial function.
It's
And by the way, polynomial implies strongly expressive up to p, so this is stronger. And in this case, we're going to have two algorithms. So there's A small and A sparse. And they are just characterized by the same two steps, but they differ on the specific sampling. So they essentially is just
Do
they-
this or that?
Sure.
This or that?
Yes, they are using these sampling strategies. Right? And then in this case, just as how before we have this basis of the monomials. In this case, we have the Hermite polynomials, and you can show that they are a basis, that they are orthonormal. Then we have exactly the same picture, the same limit. We are going to have the same result, the set of interpolators that our random features models can get is non-empty, so there's at least one solution. And then what is going to change is this second part. We'll have now that the distance between the interpolators that our algorithm chooses is going to depend on some function of epsilon, and this is for the algorithm small features, such that we take the limit of this noise to 0, then the function is vanishing. Okay. So the minimum degree bias is still going to happen for this more general case of non-real of real valued polynomials. When we choose an algorithm that does this strange thing of selecting very small weights and biases. Then I guess
By the way, so if you think about what happens there, we're scaling down everything. If sigma is a polynomial, let's say sigma is x squared or something, then w squared, b squared, blah, 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 right? And these are getting small, everything's getting small. You still want to express your function, so your A coefficients have to keep up. They kind of need to grow. Yeah.
You're back online. Oh, I have 3 minutes left of storage apparently. What
Okay,
kind of
wrap this
quality
up.
am I
The minimum degree
recording on here?
Changes
Like 40
if you're
gigs.
adding more dimension, does it? But here you're not changing the dimension, so that's well defined at least.
yes, so we
Right,
will have
because
that
it's
issue.
not a moving target.
Yeah.
Okay.
Okay, so if you notice, this result only took out the algorithm that considers the small features regime. So a question is, okay, well, what about the interpolators that these other algorithm chooses? And then I guess the answer is, in general, there is no minimum degree bias, although I'm not sure about this in the sense that they are picking a specific basis. I don't know if maybe you, like as Chava mentioned before, if you pick a specific basis, maybe you will get the same. But then they try to answer this, and is what breaks? How is one regime different to the regime? And the intuition is as follows: is let's say this is the the loss function that your algorithm is trying to optimize for. So essentially like some mean square error between the output and your target function. And this is going to be a function of these features that you have, of your train-out parameters, and of this dimensionality. And then they prove that you can decompose this as, again, some mean square error, where you're kind of transforming the features. It's also going to depend on the train-out parameters, but now it's going to depend on the size P. Okay, and then in addition, it is going to have an added term that is of this form. So it's a quadratic term that is weighting the train-out parameters with some matrix, with a metric in this space of train-out parameters that is going to depend on the training set. Okay, and so essentially, if you were to take the limit in this case and define, for example, epsilon as 1 over d, and take this limit, epsilon goes to 0, then this corresponds precisely to what the algorithm ASMAL is doing. So we know that the thing that minimizes this is precisely the same minimizer as before. Okay, but then we have this regularization term that is